Professor Dana Anderson, as I said, is the CTO and co-founder of Cold Quanta. He is a fellow of the Optical Society of America, American Physical Society, and JILA. He's also a professor in the departments of physics, electrical and computer engineering, and the director of quantum applied science and engineering at University of Colorado Boulder. Since 1993, he has been involved in guiding and manipulating cold and ultracold atoms. Dana and his collaborators, Professor Carl Wyman and Dr. Eric Cornell, the 2001 Nobel laureates in physics, first demonstrated guiding of cold atoms through hollow core optical fibers in the mid-1990s. Professor Anderson's group demonstrated the first ultra-cold atom chip portable vacuum system in 2004 and has been heavily involved in DoD-funded activities to develop ultra-cold atom chip systems. When not immersed in the continued development of ultra-cold atom technology, Dana turns to his passion for flying his Cirrus SR-22 and spending time with his family. Take it away, Dana.
Today for Cold Quanta's fifth webinar in quantum technology. It's quite common to think in terms of quantum computing whenever the word quantum alone or quantum information processing is discussed. But in fact, quantum computing is just one context of quantum information processing, and there are quite a few others, and they include, for example, quantum simulation and quantum emulation. And I want to introduce to you yet another context of quantum information processing that we refer to as quantum signal processing. And because we're Cold Quanta and our focus is largely with atoms, I'm going to introduce this topic in the context of laser-cooled atoms. Let me give you a brief overview of what you'll be hearing about today. First of all, as a fairly new arena for many of you, let me start by saying what quantum signal processing is and talk about signals in real time and quantum aspects, and then take a step back and say, in general, how we process information using cold atoms through preparing, manipulating, and measuring a quantum wave function. But atoms not only can process information, they also make very good sensors. And we use the atoms to pick up signals in the first place. So I'll talk about physical signals to process, and I'll focus specifically on using atoms for precision navigation. It's simply an example, I think a very important one, which I am personally interested in, but it's a typical example of a system that generates signals which one would like to process. The way we approach it is by placing atoms in optical lattices. There are other ways of approaching it, but I'll focus specifically on information processing using this technique, and taming and controlling atoms using machine learning in optical lattices, and then also using neural network techniques to calibrate sensors, to classify the signals of interest, and so on. So I'll start in a way that I don't normally do. I'm going to lean on the dictionary to say, what is a signal? And there are a number of definitions, and there's one that's very fitting for us today, which is all the way down in definition number 4, which is a signal is a detectable physical quantity or impulse, such as a voltage, a current, a magnetic field strength, and so on, by which messages or information can be transmitted. And yet, to highlight a contrast with aspects of quantum computing, there's another aspect of a signal which is very important that you can find in an earlier definition in the Merriam-Webster dictionary, and that it is something that incites to action. And with this definition is the notion of time and what's happening now. So you have a signal and you expect that there's in response an action. And so in quantum signal processing, one is very conscious of the real-time aspects of a problem, Whereas, for example, in quantum computing and other domains of quantum information processing, real time, or the time aspect, is often less important in the information processing per se. And you can understand what I mean by real time. I'm going to use it very loosely, but when the light turns green, if the person in front of you is not moving ahead, well, you honk your horn. There's some notion that there's a cause and then there's effect associated with the signal. So what is quantum signal processing? We've just said what a signal is, and somehow processing it, among other things, might invoke an action. What does it mean for a quantum signal process? Well, it's very simple. When the signal is quantum, and that is when the signal can be described in terms of a quantum state vector written here as ket psi of t. More generally, we can think of a quantum signal to be processed in terms of a density operator rho of t. But I'm going to focus on the wave function because for many of you, the wave function can be a bit more intuitive than the density operator. So quantum signal processing as an arena, as a topic, as an exercise, involves the generation, manipulation, and the detection of quantum signals. What's it good for? When is it interesting? Well, we talk about quantum signal processing today when one seeks to achieve quantum limited detection in a practical environment. And in a practical environment, I mean in a field where there might be noise, interference, all kinds of things that impose disturbances on the signal, and you want to get the signal and not the noise, for example. And of course, anytime the system already involves a quantum sensor, it's often more efficient and makes better use of the quantum information to process while the signal's in the quantum domain before it becomes classical or is measured and so on, and then subsequently processed. The systems I'll introduce today are quantum mechanically in many respects pretty simple. That is, they don't involve entanglement. And for the future, I think it's going to be very interesting to see what happens with quantum signal processing when we do better understand how to utilize entanglement together with learning techniques to enhance signal detection, to enhance transfer functions, classifications, characterization, and so on. But I won't touch on them much at all today. So let me give you what I think is the world's most stunning example of quantum signal processing. From a signal processing point of view, conceptually, it's pretty simple. Technically, it's not at all simple. And its importance, as I've said, stunning. And that's the Laser Interferometer Gravitational Wave Observatory, which consists of a series of interferometers, very large interferometers showing in the lower left, with very large systems of optics shown in the middle, generating a signal all the way here on the right. And this is a very significant signal. It was of the first gravitational wave detection ever, back a few years ago. And so it's appropriate to think in terms of something that's time dependent, that's important, and carries the information fitting for the definition of quantum signal processing. And in many ways, this system is very characteristic of what we're interested in. In this case, it's light-based, not atom-based, but still the same thoughts behind it. So a classical gravity wave signal is generated by a cataclysmic gravitational event, such as a binary star collapse. It emits a wave, which eventually gets here to Earth. And here on Earth, a small number of very sophisticated optical interferometers detect something truly inconceivable. They can measure a change in the position of an interferometer mirror that's equivalent to 1/1000th the diameter of an atomic nucleus in an arm length that's 4 kilometers. That's about a part in 10 to the 21. Unbelievable precision that they get by using quantum techniques and signal processing. And in the future, by the way, I already mentioned what happens in the future and our interest in entanglement. A continuous variable version of entanglement is called squeezing. And in the future, LIGO will use squeezing to increase their ability to observe the universe by a factor of about 7. So a beautiful example of signal processing, and also very characteristic. So the signal itself in nature and the environment is classical, but it's transduced by a quantum system. And then the quantum signal processing followed by classical post-processing identifies interesting and important events. So for us, let's take a step back, moving from optics of the LIGO interferometer to what we're interested in particular, which is doing information processing with laser-cooled atoms. And as I said, I'm going to take a step back. Whether we're talking about quantum computing, quantum simulation, emulation, or signal processing, we're always doing the same thing with atoms. We seek to establish exquisite control of the wave function of an atomic ensemble. And that typically involves preparing atoms, manipulating, and measuring them, which I lay out here. There's a pre-step, in our case, of cooling atoms, distilling them to turn them into a quantum state. And from there, the quantum signal processing or quantum information, whatever we're doing, takes place is initializing a state, manipulating the state, and that manipulation can be, say, by an algorithm, but in our case, it's a combination of our algorithm and also the environment. The environment is presenting the signal, and the quantum system transduces it to turn it into a quantum signal. Then there's typically a step in which one prepares the system for a measurement and then actually carries out the measurement. And from then on, the output is classical. In some cases in quantum information processing, one is interested in learning something about the wave function itself. That's usually the case for quantum signal processing. And sometimes one is interested to learn something about the Hamiltonian, for example, that caused the wave function to evolve in the middle step. Often quantum emulation is interested in that. But regardless, the process is always the same. And so that one thing is to gain exquisite control of the wave function. And it covers all of computing, emulation, sensing, and so on. So to get started, I want to talk about the first step in that. I'm going to talk about it only very briefly, and let me direct you to the YouTube versions of our second and third webinars in which we talk about laser cooling and then turning atoms into quantum state. So we use laser cooling routinely to cool atoms down to the microkelvin regime. And it's routine, but I'm still just so find it remarkable that in the space of a centimeter or so, we can freeze the motion of atoms from room temperature down to a few microkelvin. And we do so by applying forces on the atoms using laser beams that amount to about 1,000 Gs, where a G is the force that you feel due to the gravitational pull of the Earth. So enormous forces. And one thing to emphasize here is, whereas atoms floating in space, which is what they're doing, sound kind of light and delicate here, none of the stuff that I'm talking about in training, learning, processing, and so on involves being very gentle with the atoms. We apply very large forces to make them do things we want them to do. So we do laser cooling using what's called a magneto-optic trap, and then we further cool the atoms using a variety of techniques, some of them optical, some of them otherwise electromagnetic, sometimes magnetic, to get them below a microkelvin. And if you do things right, in certain circumstances, you go from a thermal ensemble of atoms to a quantum ensemble of atoms. And that's usually for us the starting point. We might be talking about cooling thousands or hundreds of thousands of atoms, or even a single atom, but a starting point are these very low temperatures. And again, I'll point you to Seth Callaghan's webinar to learn more about Bose-Einstein condensation, which is, again, typically our starting point. So once we have these very, very cold atoms, what do we do with them? And they're very at home at sensing tasks. Atoms are sensitive to all kinds of things. In particular, they have mass, and so they're sensitive to inertial forces, such as acceleration, such as those that cause rotation, such as gravity, and so on. And as I said in the beginning, my focus here is a context, and that's using atoms for precision navigation, part of a complete package of precision navigation and timekeeping. But as I said, it's simply an example. I think it's a very important one. But for those of you who are not so interested in navigation per se, there are lots of other things to do with atoms. And in all cases, it's interesting to think about how you want to process them. So atoms are also sensitive to magnetic fields and electric fields and radio frequency fields, optical fields. You can make them sensitive to sound, to speech, to what have you, usually coupled by an intermediary, say by magnetics or optics. So you can pose a variety of signals, either from the environment or intentionally, onto atoms, and then signal process. And what are we going to do with signal processing? Well, the interesting thing to think about is manipulating the transfer function of a system involving cold atoms, such that you can be sensitive to certain signals and not to others, for example. And this usually involves manipulating the atomic potential in time. And then also quantum signal processing typically involves post-processing to identify, classify, to quantify the signals of interest, just as you saw in the case of the Gravitational Wave Observatory. So to provide further context, I'm going to talk about the traditional or conventional atom interferometric inertial sensor, just to give you a reference point that provides some of the motivation, both for our approach in general, but more specifically for the kinds of information processing we'd like to be able to do on an atomic sensor. So consider that we start with an atom beam. It's a very cold beam, but it's moving. We can use laser beams to carry out interferometry first by splitting the atom wave functions into two pieces. And we do it light pulses. We can reflect an atom beam using also light pulses. And we can also combine them. The complement of the splitting pulse, we can recombine the atom wave function to become a new pair, as shown on the right. So again, I'm not going to go into detail. It's somewhat paradoxically called moving standing light fields, which are used to split, reflect, and recombine atoms. And those functions, I want you to keep in mind. Splitting, reflecting, and recombining the atoms are the key aspects of interferometry, plus the propagation in between the events. So from left to right, think of it as in time. We split, we propagate, we reflect, we propagate, we recombine the atoms in time. I thought it'd be useful to give you a little insight, if you're unfamiliar, as to how an atom interferometer actually detects acceleration. And they do so because of the recognition by Louis de Broglie that associated with any matter, with any particle, is a wavelength. And that wavelength, lambda, is determined by a constant, Planck's constant, divided by the mass of the atom and its velocity. So the slower the atom, the longer its wavelength. So a very cold atom has a wavelength about the same as the wavelength of light, for example. An atom that's in the range of less than a nanokelvin or so. Excuse me, a microkelvin or so. So I'm going to talk about the interferometer again. And because gravity and acceleration have the same effect on atoms for our purposes, we're going to consider gravity just to give you a nice mental picture rather than an acceleration. So I'm going to have gravity pointing down in the picture, convenient. And then I'm going to take a beam splitter, half silvered mirror, and put incident on that an atom that has some characteristic wavelength. Now, when it's reflected by the beam splitter, it now travels up and it has to work against gravity, and gravity is going to pull against and slow the atom down. And therefore, as it goes upwards, the wavelength of the atom gets longer and longer and longer. If I have a mirror and somehow manage to keep the atom from being affected by gravity as it travels horizontally, say by using a waveguide or something like that, well, then it keeps on going as it was with the wavelength that it had at the very top of its upward trajectory. So there it is with a reddish wavelength. I've shown it. Whereas on the other hand, looking back at the beam splitter, some of the atom wave function, so we're going to use superposition here, propagates through the beam splitter, which is made of light, by the way. But if I also manage to have it propagate horizontally, its wavelength is not affected by gravity. On the other hand, let me add a mirror now for the lower part of the atom's wave function. It's reflected, travels up, and now it too has to work against gravity, and so it slows down and its wavelength gets longer. And now I'm going to add a beam splitter. Again, we could rather call it a recombiner this time. And so some of each wave is reflected, some of each wave is transmitted, they interfere. And if there was no gravity, so the wavelengths were equal, all the atoms would come out to the right. But when there is gravity, some of the atoms will come out this other port, the upper port. And that's because if I look at the path of the atom that was first reflected, it spends most of its time with a longer wavelength. Whereas the atom that wasn't reflected at first, what was transmitted by the beam splitter, spends most of its time in the interferometer with a short wavelength or traveling faster. By the time they get up to the second beam splitter, they're the same wavelength again, but now the two waves interfere, providing different populations of atoms going to the right versus going up. And still relatively remarkable to think that a particle can be split in this way. Formally speaking, its wave function is split. And then you can witness interference for something that seems as tangible as an atom, but this really works. It is remarkable. And it's a way of measuring gravity or acceleration and configure it right. You can measure rotations, gravitational gradients, and so on. So the promise of atom interferometry is that you can use the interferometer to give you an indication of inertial forces, and the output can be extremely sensitive to these inertial forces. On the right are some equations that sort of describe the signal as a function of acceleration and as a function of rotation for a given interferometry geometry. But I won't go into those details. Suffice it to say that you can make extremely sensitive interferometers, and they've been beautifully demonstrated in the lab, but they haven't had that great success being deployed. And there are a variety of reasons for that, being deployed, say, on an F-16 or something even a little slower, such as a submarine or and so on. Now, one of the characteristics of the interferometer that I told you, I said, well, suppose we stopped gravity from interacting. The fact is that for most interferometers, they're built such that gravity acts the whole time. So in this lower picture on the left, you see these bent curves, and that's because gravity is always interacting on the atoms. And what that means, in fact, is that the sensitivity of the device, first of all, is always impacted by gravity. And as a side note, the sensitivity of the device is scaled to its size. So if you want a more sensitive device, it also has to be larger. But one point I want to make here is that often we're not actually interested in the value of gravity, only its differences. So we might like to make a system which doesn't measure DC accelerations, for example, due to gravity. That's a nice example of some signal processing I would like to carry out on an atom interferometer, is eliminate its sensitivity to DC forces, just as an example. But there are more interesting examples. Now, it's worth pointing out some reality and some realism when we talk about applying atoms to inertial sensing and techniques we'd like to do to make outstanding devices. It's just a good idea to keep a note of where the competition stands. So this is just for maintain some realism, that when we talk about using atoms in practical ways for inertial sensing, for example, rotation, we're competing with really incredibly sophisticated technology. For example, the ring laser gyroscope, which was first demonstrated in 1962 and was deployed sometime in the late 80s, early 90s. And on the upper right, you see this beautiful device. It's about the size of the palm of your hand, and it has incredible performance. It's, I think this one is better than aircraft nav, I don't remember, but it's compact, it's manufacturable, and so on. But of note, it's worth saying that if you argue that this is actually also a quantum device, and it took a long time to develop, to make it useful, to deploy it. It started out, what you see on the left is a meter on the side, ended up being something you hold in the palm of your hand, more or less. Really incredible technology. This is what we'd actually like to see with atoms, only much more quickly. So it'll take work, and this is the competition, and this is where we eventually need to go. But with that note from our sponsor, that there so far is no atom-based inertial sensing system that competes with this laser gyroscope technology, let's move on. So first of all, I'd rather atoms not be influenced by gravity all the time, and I want to gain a lot of control of the atoms. And so I'm going to hold them up against gravity and do it using optical lattices. And optical lattices are incredibly conceptually easy to produce. You simply take laser beams, you interfere them, and the interference is a pattern, and atoms prefer, for example, to be stuck where the light intensity of this interference is a maximum, for example. It could also be a minimum. So if we take two laser beams, they form an interference pattern. If I shine those two laser beams on very cold atoms, they will be attracted and combined to regions of high intensity. So this is an example of what's called a one-dimensional lattice. You can also do it in 2D and 3D. You can make simple lattices. You can make complicated lattices. As I say, conceptually relatively straightforward. For a 2D lattice, for example, you take two pairs of counter-propagating beams, and they form something like an egg crate in 2 dimensions. And you subject those beams to cold atoms, you can make an array. Here I've exaggerated a bit that one would get an atom in each spot. That's a very interesting thing, an important thing to do. But in fact, in the systems I'll talk about today, we have an atom in a trap spot every so often. So not very high population for the things I'm talking about today. And once again, it seems like all this stuff is kind of, atoms, they float in a vacuum, they're cold, and they seem delicate and so on. But when we talk about optical lattices, we're applying forces to atoms that are tens to hundreds of G's of force. That's huge. It's like mortar and bricks are holding atoms in place. And when we move them, which we will in a little bit, we likewise are moving them using very large forces. Now, if you put atoms in a lattice and the lattice is just sitting there, well, the atoms can't move. They're going to be insensitive to inertial forces. So what to do? And that brings me to introduce designer wave functions and machine learning. And this goes a long way back to, well, pretty far back to 2001, to a paper by Potting, Kramer, and Pierre Maestre. And Pierre Maestre was actually a postdoc during the time I was a graduate student working on ring laser gyroscopes. So the world crossed paths many times around. So they put together a paper called Momentum State Engineering and Control in Bose-Einstein Condensates. And to highlight, we demonstrate theoretically the use of genetic learning algorithms to coherently control the dynamics of a Bose-Einstein condensate. We consider specifically the situation of a condensate in an optical lattice formed by two counter-propagating laser beams, just what I showed you on the previous slide. So the concept is actually relatively old. So to translate what Potting, Kramer, and Meister were telling us, they said we can transform an initial state vector, or initial wave function of an optical lattice to a different desired state by appropriately shaking, or maybe more correctly said, modulating the lattice. So we start with some initial state vector psi sub I, and we want to transform it to some desired state vector psi d, psi desired, and we can do that by shaking the lattice. Now, it should be, unless you've thought about it already, this should be incredibly counterintuitive, in my opinion, that you can put atoms in a lattice, say the ground state is typical, and now you want to change the wave function of those atoms to something you desire. You can do it by shaking the lattice. So if you feel that's weird or not reasonable, that's perfectly understandable. And if this is your first time indeed, I wouldn't expect you, and I don't think you should either, to understand really that it can and how it should work, but it does. And one can determine how to shake the lattice through a learning algorithm. You can use genetic algorithms, and we have used genetic algorithms, Korotov method when you're simulating this shaking on a computer. Experimentally, we've used the Crab algorithm and a modified Crab algorithm called dCrab. You can use neural network techniques and so on. Most of what I'm going to tell you comes out of work first carried out by Dr. Carrie Widener, who was formerly at the Gill Institute, is now Gill Institute at the University of Colorado. She's now at our House University. And here's a paper, which what I'm telling you is based on, called Atom Interferometry using a shaken lattice. So we start with Potting et al.'s idea that you can use a shaken lattice to control a wave function. So what kind of wave function do we want? Well, you saw that interferometry, which is what we're going to emulate, started out by taking atom beam, a wave function described by a wave function, and splitting it into two. So splitting actually is a key function of carrying out interferometry. It is the center of mass version of superposition that proves to be so powerful in quantum information processing. So just to say how we do it experimentally, it's very easy to measure the Fourier power spectrum of the state of the atoms in a lattice. And that's because the power spectrum is discrete. And you can literally take pictures of the atoms by releasing them from the lattice, letting them fall, and using a camera and a laser beam and taking their snapshot. And if you do that, and you start out with atoms very cold, they'll be in the ground state of the lattice, and you'll get a number of clouds that might look like this. Each of these is a cloud, and they're discrete, and above these, you see -4 P0, -3 P0. The P0 is the quantum of momentum equal to 2 times Planck's constant times, it happens, the K vector, or roughly speaking, 1 over the wavelength of the laser light you're using. And so you get this discrete spectrum, and from this, within phase factors, you measure the wave function of the atoms. And the ground state might look something like this, where the 0 momentum state, meaning the atoms don't have any momentum, is highly populated. The plus and minus 1 units of momentum are less populated, the plus and minus 2 are less populated, and so on, and probably no population in 3, and by 4 units, not much population. Okay, that's the initial state. What's the desired state? Well, it's split, and we'd like 2 clouds propagating in opposite directions. That's 2 clouds of some value p and some value minus p. So this is what we want. Well, that's the square of it. All population 0 except for those 2 clouds. So if we shake the lattice, think of marbles in an egg crate. If we shake the egg crate, we'll get the marbles to move, right? And start kicking around and so on, and I'll impart momentum to them. Well, I want to be a little bit more careful about how I do it, but using a learning algorithm, I want to minimize, roughly speaking, an error that assesses the difference between what I got when I shook it and what I wanted, which is the split state in this case. So we build an interferometer shake by shake. So this was just the first step of going from the ground state of a lattice to a split state of equal and opposite momentum. So here's with some license, a figure, a graphic that shows a lattice. It shows a cloud of atoms. You know, if you drill down on this, these pictures are terrible lies, but for our purposes, they'll do to tell the story. And formally, the lattice is described by this potential that you see here. V of x and t is given by some amplitude times this cosine 2kx plus some phase. And this cosine is just the sinusoidal interference pattern. I'm moving my fingers, but you can't see them. While this phi of t is the phase, it tells you where the nodes and antinodes of the lattice are in position. And when I shake the lattice, it's this phase that I change. So this phase is controlled. The atoms occupy several momentum states. I want to change that to occupy just 2. And in fact, to do interferometry, there's a series of steps I want. First, I want to shake the lattice, as shown here on the right. They start out in the ground state. I want to shake the lattice so that the cloud is split into 2 equal and opposite moving clouds. Then I want to allow the atoms to propagate. But propagating momentum states in the lattice are not stable. You have to shake the lattice again so that the atoms can propagate without disturbing their wave function. And then you want to figure out how to shake the lattice to turn the atoms around to go the other direction. That's reflection. Then you need to propagate again. So you have to shake it again differently. And finally, you have to recombine them. So what you're seeing on the right here is all the steps of interferometry: splitting, propagation, reflection, propagation, and recombining. And each one of those involves finding a phi of t that performs the task at hand of going from the initial state, which might be, say, momentum states propagating outwards, to a final state, which is, in reflection, reversing the momentum. And each one is a different shaking routine, and each one has to be learned independently. Now, for experts, to give you some insight in why this is not crazy, is that the states of atoms within a lattice are described by block functions and are characterized by, for example, this diagram here, which shows energy versus quasi-momentum. I guess this is experts. And the energy gaps between these states, in particular those states that are at 0 momentum, tell you the frequencies of shaking the lattice which do something interesting, which make resonant transitions. And that will begin to give you a glimmer of how you can possibly manage to go from one state to another by shaking the lattice, with the other statement being, again for the experts, that the modes of a lattice are a complete set. So in principle, you can change from any initial function to any final function by appropriately modulating the lattice. So we use this understanding of the physics of atoms and lattices simply to help us learn. And in real life, anyway, in an experiment, you don't know things well enough to be able to do shaking without the learning. So for example, we learn how to shake again to split atoms from a ground state into oppositely directed clouds. So we can teach the atoms, or they can say they learn how to become an interferometer. We start with an initial state. We set up some learning, machine learning algorithms, and we go through a set of steps. For example, so we have a computer. It applies classically a shaking function. It tries a shaking function, says, I'll try this one. Let me try it out. And let me see what happens. Oh, well, I get 4 clouds, not 2. And therefore, that's not what I want. Let me now modify the shaking according to some algorithm that I like. And eventually, I get what I want. After that, the system has been trained. It'll work day in and day out, provided nothing dramatic has happened to the instrumentation. So once the shaking function is known, it's fixed. And as I said, this is a splitting one. In fact, there are 5 steps altogether. And after I've trained it, then I can calibrate it. And so, for example, if you look at what happens to the wave function after it's learned, but while it's being split, I have this diagram here. On the left, what you see is momentum on the vertical axis going from 0h bar k to 8h bar k. On the horizontal axis is time. And I start in the ground state of the wave function, and the population is indicated by the color. So most atoms are, on the left, are in the 0 momentum state. You can't see much in the 4h bar k, but there is some in the plus or minus 2h bar k. On the right, we want a split state of just 2 momentum states. And after you've learned the shaking function, you can say, what's happened to the wave function? And the answer is, well, it's complicated and it's not unique. But in the end, you get what you want as a split state. Now, one of the beauties of doing this interferometry is you can change the interferometry sensitivity by simply extending how long the atoms propagate. If they propagate longer, it becomes a more sensitive interferometer. Shorter, a less sensitive interferometer. So you can tune its sensitivity simply by extending the propagation time. And if you want to know what things look like experimentally, this is taken from a paper by Carrie Widener. It was done a few years ago. And this is a picture of atoms after they've been split. And you see it looks a little cruder than what I showed you, but you see 2 clouds and they're split. And this is after an interferometer sequence, the lower one here, after they've been recombined. And using a little post-processing, you can tell what you're doing. In this case, the learning was to about as good as about 5% and 2% in the lower case, about the training of how well you do to control the momentum states of the interferometer. So using this concept of putting atoms, cold atoms in a shaking lattice, you can do lots of things. You can put them in general 3D lattice. For example, and you can make a gyroscope. Instead of making atoms go back and forth, as we did with the 2D lattice, you can make them go in circles and make them sensitive to a rotational motion. In this red picture I've just shown, in time goes down, the sequence, again, of an accelerometer, starting at the top, you have the initial state, you split the atoms, you propagate them, you return them. And as I said, by changing the propagation time, you can vary the sensitivity. But you can also do things like look at gravity spatial gradients by the way you sequence the events and the training. And you can even make something that's insensitive to DC accelerations, as I mentioned, by simply changing the sequence of events that only time-dependent signals will be picked up by the atoms in the interferometer. So this learning is a very powerful approach to making a sensor. Well, that's the learning. What about afterwards? You apply a signal, what do you expect? Well, if there's no acceleration of gravity signal, then after the whole interferometry process, you end up with what you started with, which is shown here, where it says A equals 0 for acceleration equals 0. And above you see the labels of the momentum states. But after training, you have to calibrate the system. So you apply different accelerations and you look at the patterns that come out. And now we apply neural network techniques such as independent component analysis, or you can use recurrent neural networks to track the history of the system to associate with a given output what is the most probable input. Or you can do further training to stay on a null, as many instruments do. Gyroscopes are often operated so they're always operating near a 0 and canceling out the background signal. So you can do that here as well. So this is just a slide that shows a typical calibration technique, but these concepts actually go back to also a number of years ago. In fact, a number of years ago, we carried out some of the first analysis of on-chip interferometers. Here they only have 3 momentum clouds in this case rather than 5 or 7 or what have you, using independent component analysis and related techniques that sort of grew out of the second wave of interest in the neural networks in the late 80s and 90s. So we used that to determine what the interferometer was doing. So I said pretty well-established techniques to analyze cold atom systems to understand the inputs to those systems. So I've introduced you to quantum signal processing, the use of machine learning of atoms and optical lattices, and the use of neural networks, particularly to do post-processing. And I've done it in the context of quantum signal processing, which, as I mentioned, entails the generation, manipulation, and detection of time-dependent quantum information. And we have shown how quantum signal processing can be applied to detect inertial force signals using atoms in an optical lattice. But the fact is, one can consider processing essentially any time-dependent signal as long as the time dependence lies within the bandwidth of the system by applying such signals to the lattice itself, or by applying them to magnetic fields, which will also impact the atoms. And you can do more sophisticated things. But the point is, the approach enables one to leverage the substantial sensitivity of atoms, and atom interferometry in this case, in detecting and also classifying signals of interest. And one thing I want to point out is modulating optical lattice is simply one approach to signal processing with the help of machine learning. Generally, one seeks to dynamically change the potential landscape seen by ultracold atoms to process more generally. So to wrap up, the use of machine learning and neural network techniques for quantum signal processing, it's in its infancy. It's nowhere near, for example, where quantum computing is in terms of the people putting energy, thought, and development into it. So we've only scratched the surface, and I've only given you an introduction. So we hope you find it interesting, but I also want to let you know that over time, CoQuantum will be providing you with tools where you can also explore and further develop such signal processing techniques yourself. I appreciate your time, and I welcome questions. Thank you very much.
Thank you for a great talk, Dana. That was fabulous. We got a few questions and more coming in right now. People are asking more and more questions. So Ed asked early on in the talk if the split and recombined atoms are in vacuum, or if they are in a matrix of in a background gas of other cold atoms.
Ideally, they're in a perfect vacuum. No vacuum is perfect, but that's what we intend. So there's finally a finite lifetime of the quantum lifetime of the atoms, and that, for example, a good number is, depending on the system, anywhere from milliseconds to seconds.
All right, great, thank you. And Joe asks, what are the principal sources of noise in an atom interferometer? He's wondering if you could roughly order them in magnitude and impact on the final measurements, from such as the state preparation with lasers. Is the phase noise and pulse length important, or does more of it come from the detector at the end and interrogation of the final state?
Oh, that's a great question. And let's ignore the environmental noise of sitting in an F-16 for the moment. First of all, you have fluctuations in atom number, although in fact that can be revealed by the post-processing that you do. And those fluctuations come from a variety of technical imperfections in presenting laser cooling. And then in the end, the way the atoms are captured into the lattice. Right now, there's no further cooling to the ground state, so that introduces noise. Shaking is not perfect, so that to some extent the atoms will interact. They'll collide if you don't have sparse population, and that will cause heating, and that heating turns out to produce noise in the imaging. I'm not sure I want to pick out the biggest one at the moment, but I would say in the imaging, it's not the detector noise, it's the number of atoms due to that background heating. There are also, by the way, noise effects due to the imperfect, say, intensity fluctuations of the lattice, but that can be controlled relatively well. So at the moment, I guess I'll rank up there things that then end up giving you inconsistent numbers of atoms in the images.
All right. Manuel asks if the genetic algorithms or machine learning algorithms need to consider the effects of 2- and 3-body collisions and how they are included in the models.
Oh, that's great. Experimentally, we try to avoid that regime. We don't entirely, so there are collisions. It's incredibly difficult to incorporate collisional effects in learning. If you try it in simulations, you'll find that out very quickly if you don't already know. But you'll notice the paper by Putting even considers interactions through Gospodyevsky. So provided they're consistent, you can deal a lot with interactions experimentally by the learning, but making the consistent is a trick. And this will look forward to what we're very, very interested in, is making use of interactions, in particular interactions which lead to entanglement, to enhance our ability to either detect signals or to carry out the design of the transfer function. Great question, and I hope there are a number of people out there that want to go out and explore this more. Collisions are really non-trivial to deal with.
He continues with another question about the complexity of the searching space as the size of the lattice grows. The Hilbert space should increase exponentially with the number of atoms. How does the machine learning algorithm handle this?
Oh, that's an extraordinarily good question. And the fact is, as I implied, but I'm going to make it explicit. When we currently do our experiments, we are working in the circle single particle regime, which means there are no interactions, which means the Hilbert space is not scaling. And that's because we don't understand yet even how to address your question. And we're looking forward to getting enough understanding again so we can make use of it. But it's a fascinating aspect of quantum signal processing. And we look forward to getting a greater understanding with the help of the community in the future.
All right, splendid. So Joe had a follow-up question on his earlier question about the noises. And he's wondering about the difference in between using a thermal beam and a lattice configuration with the cold atoms.
Good question. So the lattice, first of all, assumes and requires quantum aspects, center of mass quantum wave functions. And that means quantum gas, that means essentially arbitrarily close to zero temperature. You can also use a thermal beam. Thermal beam has advantage of very high atom flux. So for Joe, since I know which Joe it might be, you improve with the square root of n. But the beauty of working the quantum regime is you can integrate, in principle, for arbitrarily long, or at least long as the coherence time of the atoms, and you typically gain as the interrogation time. So you lose an atom number typically when you work with the ultracold, but you gain an interrogation time, and you also gain in the functionality of controlling the transfer function, which is quite hard to do in the thermal beam case. I hope I've answered your question.
I think that was excellent. Andrew asks about one of the diagrams that you showed, that it shows the quasi-momentum, the block states, and he thinks they look similar to the conduction bands of a semiconductor and wonders if there's an analogy to be made between shaking the optical lattice and some existing techniques done in semiconductor physics or photonic crystal optics that can give us some intuitive insights or analogy to what the shaking is doing.
Well, I think the answer is, you're darn right. There's completely related, and much of the interest in quantum emulators using optical lattices is exactly like that. People are interested in studying, for example, high TC materials using atoms and lattices as surrogate medium where they can be pure and you can control them and so on. If you have further insight, so we do use the model to get insight into what shaking does, and we use it to help inform how we should learn. And I think that can continue. If you have additional insight, we would love to hear it. But the bottom line question is, yeah, they're completely analogous, and what you know about one thing can be translated to the other.
All right, great, thank you. I think we have reached the end of the webinar right now. So thank you again for your presentation, Dana. And thank you everyone that attended, and thank you for your questions. They were great. We will reach out to the ones that asked questions that we didn't get to, and chat with you about them. Thank you all for coming.
Bye-bye.